Am I audible, guys? My voice is coming up fine. My audio and video both are okay. Just type yes on the chat window. Okay, so we'll give it a couple of minutes. Let me check how many people are there. So I have 15 of you. So we will need to wait for some time, 2-3 minutes, because I have around 120 acceptances. Let me put a reminder in our WhatsApp group. Okay, please put your comments. I will be constantly checking it. Might not be that at the very instance you put your comments, I will be able to check. And please maintain the decorum of a public chat. My earnest request. Otherwise, this will be easily hijacked. We are here with a purpose. Let's solve that purpose. Let's see if we require the entire 3 hours. If not, we will wind up early. Okay, so let me start off and let others join. The first part is not that important. I think it's more theoretical, so people may catch up. I will just check the comments once. Yes, I will provide you with the PPT. And this PPT will have the answers of what we are discussing. There is a lot of discussion questions. There is a lot of discussion topics. And not necessarily all of them will come for your CA3s. But then, of course, it has been created with the context of what has been taught in your classes and what is important from a examination perspective. So it will have questions which are important. It will have questions which may not be important from the examination perspective, but definitely is important from your semester perspective. So the PPT will have that. Ushnik, your question about questions from DSA, let us go through the topics that we will cover. After that, even if you have a doubt, we will solve that question. But then please go through the topics that are being discussed. It will give you a guidance of whether we are expecting more of application-oriented questions, theoretical questions, or programmatic questions, programs that are required. First of all, programs, as I said in all my classes, programs will never come or should not come because it's a DSA algorithm. So algorithm means that you are supposed to write an algorithm and not a code, not a program. So this theoretical paper never should have anything to do with program writing. It is everything to do with algorithms, and you will see that my lecture here will cover mostly algorithms only. None of them, some of them may be programs, but mostly it will be algorithms only. And even if they are programs, you can write algorithms in lieu of it. Now, algorithms will come more or theory will come more. Let us see how the lecture is structured, and then probably you will understand. Let's start off. How many people? Let me just quickly finally check, and then let me start off. Okay, I see only 17 of you who are here. I'm not sure if I'm checking the correct statistics. Views shows 52, live viewers shows 17. I'm not sure how to read that. But then let's start off. I don't mind whoever has not joined, let them not join. So we start off with the following things to discuss today, which is on the algorithms and their time complexity. We will try to finish this off quickly. Asymptotic notations, which we had already discussed in our classes, and we will continue to discuss this. Not too many questions may be expected on asymptotic notations, but you need to be aware of certain things on asymptotic notations and how they tie up with the best case, worst case, and the average case time complexity. We will get into stacks, which is our first ADT, the abstract data type, and we will solve a lot of stack related questions. Then we will get into the other ADTs, which is queue, linked list, which we will also include a double linked list. Some of you may have double linked list in your syllabus, some of you may not. Remember that this session is being conducted for all students across West Bengal. So it may be different colleges who may be joining. Hence, I've tried to get the syllabus as a union syllabus, which is relevant for all of you. Then we have the binary trees. We'll wrap it up in the binary trees. I intend to finish this till this portion by 3:30, so that we will be on time. Let us see if I can do that. So we get into algorithms and time complexity. The initial part of algorithms is a theoretical concept. You need to remember three things on algorithm. What is an algorithm? Means it is finite, right? It has to be solved in a definite amount of time. That means it is one of the characteristics also of the algorithm. It is a step-by-step, unambiguous sequence of instructions. So that is the second property, which is this. It is a well-defined. It should be well-defined, means there should be step. You cannot just say boil the water till it becomes hot. Now that is ambiguous. Hot may be having different meanings for different set of people. That's why it cannot be ambiguous. It has to be unambiguous. That's the second point. Solve a problem. It has to solve a problem means it has to have a well-defined set of input and an output. Now, input can be 0 to an algorithm, which is very important for you to understand. That there could be a question which says, can input be 0, output be 0? So we have to be careful there, and we will talk about the input being 0, because without input also we can run a program, but a program will always produce an output. And from an effectiveness standpoint, all algorithms must be simple enough to be executed, which means that you cannot just say, go to the moon and come back. That is first of all, it's ambiguous and it's very unrealistic. So ideally, by a machine or a human, you cannot execute that algorithm, which is why the algorithm has to be an effective algorithm. So the characteristics of the algorithm are part of your definition in some way or the other. How you want to remember this, up to you, but this is an important aspect from an algorithm standpoint. Let's move on. The types of data structures, two things are important here. One is that these non-primitive data structures, you all have been working with this data structure in your C days, where you worked with integer, float, character, boolean. These were your primitive data structures. Now you have grown up, you are now working with non-primitive data structures. And in these non-primitive data structures, you are working with linear data structures as well as non-linear. Linear you have covered arrays, linked list, stacks, and queues. And non-linear, you are starting with trees. So all of this you know, but remember the categorization here. Which ones are linear, which ones are non-linear, and of course, this is very important. What is the difference between a linear and a non-linear data structure? I have kept it as a bare minimal difference, only 3 differences with 1 example or 2 examples. 3 differences. Linear means they are sequentially, like things are stored sequentially, whereas in a non-linear, they are hierarchically or connected. Trees, you know how they are connected. You have seen trees by now, so you can understand hierarchical connection or interconnections, not necessarily sequential. And because they are not sequential, the traversal can go from one branch to any other branch, not necessarily the next element. Whereas in a linear data structure, you will always have to go either forward to the next element or backward to the previous element. You cannot jump elements. And because of this, linear data structure is very less flexible, and non-linear data structure is more flexible because it has a dynamic allocation in terms of the branches getting created dynamically, and hence gives you the flexibility to branch in, branch out. So those are the 3 important differences. Please read them, and of course, give 1 example in case this question comes up. Don't forget to be cautious about this line also. If the elements, this is taken from your PYQ, if the elements of a data structure are stored sequentially means, of course, we are talking about a linear data structure. Do not say this is an array, then it is an array. In the class, when I discussed this, some of you said it's an array. Yes, it's an array, yes, but it could also be a linked list, it could also be a stack, it could also be a queue, because the data is stored sequentially. Right? If the data is stored sequentially, you just can't say it is an array. It can be a linked list, stack, or queue. Hence, it falls under the category of linear data structure. Right? So that is on the data structure categories and how you will distinguish between linear and non-linear data structure. Do not forget this. If it comes, please do not write arrays. Next. I will be checking the comments once I finish algorithms. Every module I finish, I will check the comments, and then we'll spend 5-10 minutes on the comments and come back again. So a lot of you do not probably understand how to write an algorithm. I thought that it is important for you to understand how to write an algorithm. This question has been intentionally put. It will not come, I'm telling you right away. This has been intentionally put to explain you how to write an algorithm. It can be written like this, it can be written like this, or it can be written like this. So we start off by saying that we are not writing a code. This is not a code. This is an algorithm. So my style is I say a underscore the function name. That is algorithm underscore the function name. So that people are aware that I am writing an algorithm. It's not a code. You can also write the whole word algorithm underscore function name. Right? So that you can do. That's not stopping you. Right? So, but I will write this like this, and I will anyway say this is the algorithm at the top so that people are not confused. But from a coding, from a representation standpoint, I would prefer you do like this. Right? A underscore the name of the function. And then you can do a step 1, step 2, step 3 approach. You can do a begin end approach, or you can do a simple neither step 1, step 2, just write what you feel with a start stop. Right? So remember that you can say that set fact equal to 1, or you can also say that fact reverse arrow equal to 1. Both are the same. So in an algorithm, this reverse arrow means 1 is going inside factorial, or you have the standard writing as in code that fact equal to 1. Irrespective of what you write, even if you don't say fact equal to 1, even if you don't say fact arrow 1, and just say that we will put fact as 1, write it in English. You can write something like this also. You can replace this statement by saying set fact as 1. This is also perfectly legal. As I said in my classes, that there is no syntactical compliance for you to write an algorithm in a particular manner. Whatever comes in your mind, write it in English. As long as it is logical, understandable, it can be used. I have just given you 3 different styles. You can have a 4th style, 5th style, 6th style. It doesn't matter. Use it. as long as it can represent this way, that there is a for loop, there is a fact that is getting calculated, there is an output that is coming out at the end, right? You should be fine with that. So that is on the how to write an algorithm. Now we'll get into the complexity and order. Now in the complexity and order, in my initial set of classes, I had told you that let us say that my code is this. When I say my code is this, it takes 2 milliseconds to run with an input size of n on my code. So if my code has an input size n means the input variables are can be a particular number. Let's take an array, right? So the input variable has an array of size 100, which means my n is 100. So with that n100 array, right? If I run the code, whatever that code is, it could be a linear search, it could be anything, anything that I am running the code. I see that at 2 milliseconds, every time I run it, it takes 2 milliseconds. No matter I change the value of n from 0 to whatever value I want, right? I change the size of the array. I change it to 10 blocks, 20 blocks, 30 blocks, 50 blocks. Here it is still 17.5 blocks or 18 blocks, right? I will still be getting my output in a constant time of 2 milliseconds, right? So which means that it has this n, the size of the array has no influence on the time that is taken to run my program. Which brings me to the conclusion that if now I put the same algo, this is my algo, I put the same algo in a slow machine, then I will take 3 milliseconds probably, right? So with let's say 1 as n, I might take 3 milliseconds. Earlier I was taking 2 milliseconds. Now I'm taking 3 milliseconds because I put it in a slow machine. But then that slow machine will always produce 3 milliseconds irrespective of the size of n, right? The actual my own machine produces 2 milliseconds, the slow machine produces 3 milliseconds, and a very fast machine produces 0.5 milliseconds. What does it prove? It proves that, of course, the time taken, actual time taken, the value of time taken is going to change. The value of time taken is going to be something which will be dependent on the hardware of the machine, which is understandable. Somewhere it will be 1 millisecond, somewhere it will be 2 milliseconds. But what is happening is that value remaining constant with n, or is it changing with n? We see that it is remaining constant with n. So then, instead of saying that my value is 2 milliseconds, my algorithm performs at 2 milliseconds, I will say that my algorithm performs at an order of 1, right? So theoretical complexity is what we talk about as asymptotic complexity. And therefore, from the millisecond, we translate it into an order. Instead of saying milliseconds, we will say order. What is the order? Order is 1. 1, why? Because it does not change with n. If it would have changed with n, I would have put n square, log n, etc., etc. Right now, I'm saying all these 3 graphs represent an order of 1 graph. This is the number of steps. So number of steps, that order of 1, this 1 is actually saying that probably the entire operation can be done within 1 milliseconds also if I put it on a very fast machine. So, right, so this 3 milliseconds can become 1 millisecond if I put it on a faster machine. And that 1 millisecond probably is represented like this, right? So that's why even if I say order of 1, even if this 1 represents a millisecond, it will always be true because that 1 millisecond will never change. So from a standardization perspective, 3 is also 1, 5 is also 1, 5,000 is also 1. When I say 5,000, 5,000 milliseconds, 5,000 seconds, the absolute value of time is always equal to order of 1, right? Because it does not change with the value of n. This is something that you need to understand when we talk about order of an algorithm. So if we give you a problem, what is the search complexity of addressing array elements through direct addressing or index base, right? So what we are saying is, if there is an array like this, and this array is of size 10, and I want to access ARR of 5, right? Will the time taken to access ARR 5, let's say it is T1, will it be same as the time taken to access ARR 7, T2? Of course, it will be same, because you are trying to access a memory location through this particular ARR5. How? ARR5 is nothing but star of ARR plus 5. And ARR is what? ARR is the starting address of the array. Let us say it is 1000. So basically what you are saying is, you are saying 1000 plus 5, which is equal to, let's say 4 bytes, 5 4s are 20. So this is equal to star of 1020. So you are trying to go into a memory address which is at 1020 and trying to address. You are trying to go into a memory which is at 1020 and trying to get the content of that particular block. Now compare it with ARR7. ARR7 is what? Star of ARR plus 7. And star of ARR plus 7 is what? Star of ARR plus 7 into 4, that is 28, which is equal to star of 1000 plus 28. That is equal to star of 1028. So you are now saying that go to 1028 and access this element. Do you think it will be different? These two accesses will be the same time. I will access 1020 in the same time as I access 1028. Therefore, this question which says search complexity of addressing array elements, I'm accessing an array element like this through direct addressing. Direct addressing means I can do direct addressing like this, star of 1028, or through an index-based addressing like this, because this eventually will convert into this, right? So that's why I'm saying that either direct addressing or index-based addressing will take what? What is the search complexity? First of all, understand that it is constant time. If I access this and I access this in the same machine, it might take 1 millisecond here. It might take 1 millisecond. It has to take 1 millisecond there because it's the same machine, right? It doesn't change by the memory location. If I access 1020, I will take 1 millisecond. If I access 1028, I will also take 1 millisecond. Both of these are the same. 1 millisecond is same as 1 millisecond. I put more and more array pockets, it will still be 1 millisecond. That means that it translates into what? It translates into an order of 1 because it is constant time. Every time you do it, constant time is coming out. It does not change with n, the size of the array. It doesn't change with that. All it says is, I will always execute yourselves with a constant time. Wherever you want to go, I will execute it with a constant time. That means the order of this algorithm or this access is going to be order of 1. So that was on this order of 1 concept. Similarly, if you now go forward and say that, can we create a situation where we talk about an order of n access? So can we create a situation where we say that instead of it becoming constant, it will be an order of n, which means as I increase my n, you see here, as I increase my n, my time is increasing, right? So it is not remaining constant. So the time here is increasing faster. That means this is a slow machine. The time here is increasing slower. That means this is slower than this. And the time here is much more slower, right? So that means if the time is slower here, that means this machine is working faster, right? So because we are taking less time here, this machine is working faster. This is working a bit slower, and this is the slowest machine. But the same algorithm is running on three different machines and producing these kind of graph. So do you think that if the same algorithm is running on 3 different machines and producing this kind of graph, do I need to be worried about the slope of the graph? I don't need to be worried about the slope of the graph because I can directly say that my algorithm will be dependent on the size of n. That's all, in a linear manner. So I will say both the things. I will say n and I will say linear manner. That is how I will define my algorithm. I will say that my algorithm depends on n and it depends on n in a linear manner. Linear manner means line. Line means y equal to mx plus c. Right? This is what I'm trying to say. All of this is y equal to mx plus c. This is also y equal to mx plus c, only m will be different. This may be m1, this may be m2, etc., etc. Right? So if all of these are the same line curve, then I will take the highest order of my x. In this case, my x is n, highest order of 10. So basically what we have is this particular graph represents time equal to, let's say, m, n plus c. And n here represents this input. right? So what is the highest order of n here? N in highest order is 1. So that's why I will say my time complexity, that is T of n, is equal to order of this n to the power of the variable that you see here, which is 1 here, to the power of 1, which means order of n. So the highest order of this expression will be the order of which the particular polynomial will be holding good. That means I am saying I don't care about your slope. I only know that you are changing with n and you are changing in a linear manner. That means your order is Tn is equal to order of n. That means you depend on n in a linear manner. So your curve will always look like this. I don't care about the slope. Every time I execute you, whichever machine I execute you, you will follow a straight line curve like this. I am not worried about the slope. The order will be the order of n. Now, if that is understandable, then what I'm trying to get at now is, what is an example of order of n? Example of order of n, let's say, is bubble sort. Let us say that this array is already sorted. You remember bubble sort from your C days. Just go back 6 months. Right? So this particular array, 23, 35, 50, 51, 54, 69, 90, all of this is actually sorted. Right? So all of this is actually sorted, and therefore the bubble sort doesn't need to actually do the second pass. With the first pass itself, when it checks 23 with 35, it will see that 35 is greater than 23. So it will do nothing with it. Then 35, it will check with 50. It will see it is greater. It will do nothing with it. In this way, it will keep checking all the elements and do nothing. And because in this entire iteration, it does nothing, it understands that the array is already sorted. Right? If it would have done one swap, then it would have gone to the second iteration. Every iteration, if it actually does one swap minimum, it will actually do a second iteration. So that is why I'm saying that in this case, we will have to assume that this bubble sort algorithm will not go to the second iteration. It has only counted this. How many times? There are how many elements? 6 elements. How many checks did we do? We did 5 checks. What is this? This is n minus 1, because n was 6, and for 6 we did 5 checks. So we have done 5 checks here. 5 is the complexity that is coming out. And if 5 is the complexity that is coming out, then we can say that my time n is equal to, actually we will say like this, that the time taken is equal to n minus 1 swap, time taken for n minus 1 comparisons, not swap, n minus 1 comparisons, because we are doing n minus 1 comparisons and coming out of the program. So that's the time taken for the entire piece of code. So time taken is n minus 1 comparisons, right? Time taken is for n minus 1 comparisons. Now, n minus 1 comparisons can take n number, n, x, y, z, whatever time it can take depending on the machine. So I don't care about the machine. I don't care about what amount of time. What is n minus 1? Can I write n minus 1 in the form of y equal to mx plus c? Of course, I can write it. Why? Because this n is actually my x, right? And my m is actually 1. So I can write 1n minus 1. So this is my m, this is my x, and this is my c. Right? So I can write this as y equal to mx plus c. So if something follows y equal to mx plus c, what is the order? Order is order of n. So that is the answer to this question. What is the best case time complexity? Best case means what? Everything is sorted. Bubble sort doesn't need to do anything. Right? So everything is sorted. Everything is sorted means what? Still it has to go through each and every element, right? And make a comparison to make sure that it is not swapping anything till it reaches the end. That means it has done n minus 1 comparisons. N minus 1 comparisons means order of n. Right? So that is the reason why bubble sort best case complexity will be order of n. So I explained to you order of n, and I explained to you an example of order of n. I've explained to you a constant time. I've explained to you an example of constant time. And likewise, we can go on and on. There is n square, there is log n, etc., etc. Now, linear search is something that you have already done. So I'm not going to go through this algorithm. I've kept this algorithm for you to just have a look if you want to from a question perspective. The question says, write the algorithm of linear search and calculate the time and space complexities. So if I go and calculate the time and space complexities of linear search, what is linear search? Let's say I am searching for 23. If I'm searching for 23, I have started a loop with I equal to 0. So immediately at I equal to 0, I get 23. So that means I take one comparison into the amount of time it takes for one comparison to solve this problem. That means my best case time complexity is T best equal to 1 unit of time. And 1 unit of time will always be 1 unit of time. Therefore, T best in terms of the order will be order of 1. So this is 1 unit of time, and this is the order of time. This is the value of that particular comparison, and this is the order. We are converting the value to the order because 1 is a constant. So we will say order of 1. What is the worst case? The worst case is simple. The worst case is going to be T worst is equal to, let's say, I am searching for 46. 46 is here. So I has to go all the way from 0 to 6 in order to get to that particular element. So how many iterations it did? How many searches it did? It did 7 searches, right? So my worst case is that it will do 7 multiplied by the amount of time it takes to do one comparison. And that translates again to what? An order of n, because 7 is what? 7 is dependent on the size of the array, right? If there were 20, then it would have gone till 20. Worst case means it would have gone till the last element only has that. Then worst case means it will go till 20, right? So it has to be an order of n. 7 is what? N. Therefore, order of n is my worst case time complexity. And for my average case time complexity, I will have to assume that each time this particular element will be searched or any particular element will be searched. So let's say average time complexity will be time taken to search element number 0 plus time taken to search element number 1 plus time taken to search element number 2. Because you don't know where the element is, you are taking an average of, as if any of these elements would come, means average of all the searches divided by the total number of elements. So if I do the average of all these searches, what will come? First search will take 1 unit of time. Second search will take 2 units of time. And likewise, this will take 7 units of time. So you have what? 1 plus 2 plus 3 plus whatever 7 divided by 7 is your total number of elements. That means you get an average time here, which is 28 by 7, which is equal to 4. So 4 units of time is the average time that you need. Now, how is 4 related to n? 4 is related to n as n by 2. If my n is here, what? N is here 7, right? So I'm saying that 4 is related to n as 7 by 2 because approximately I can say that 7 by 2 will be 3.5. You take a ceiling of that and you will get 4. So my T average is going to be n by 2. Now this is the amount of time. Don't mix it with the order. This is the amount of time. Now if time is n by 2, can this be represented as a straight line graph? It can be represented as a straight line graph because I can say y equal to mx plus c and I have n by 2. So n by 2 means n by 2 plus 0. That is equal to half of n plus 0. So this half becomes my m. This n is my x and this 0 is my c. So y equal to mx plus c again. So if n by 2 is coming as time, then the order should be order of n. So whatever time you are getting now, convert it to an order by classifying it into a polynomial. We are classifying it as a linear polynomial, hence it is coming out as order of n, right? And by the way, if you talk about the space complexity of this, the space complexity is going to be an order of n because you will need that many number of spaces or blocks in the array to store 7 elements here. 7 is n, so order of n. So my space complexity has to be an order of n. So that's on linear search. On binary search again, this question says, write the preconditions and algorithm of binary search. Algorithm is here, right? I will not explain algorithm. We do not have time in 3 hours to go through each and every algorithm. You have my lecture videos. If you want to see, go and see the lecture videos. You will see that the algorithms have been explained at length. I have put down the algorithm for your easy reference, right? Now, if in binary search, what do we achieve? We do a divide and conquer. So we keep on halving the array till we actually reach a single pocket array. And that is where we say that we have either found it or we have not found it. And that way, we are actually reducing the search of linear search. Linear search takes how much? If you see, worst case time complexity of linear search is order of n, right? So worst case time complexity is order of n, and the average case time complexity is also order of n. So that is where the problem is, that it takes n. If it is a 1 million record array, the search complexity is very high for a linear search. That's why we opt for binary search, which gives us a logarithmic time complexity, right? So the time complexity reduces drastically when we do a binary search. But what is the precondition? It comes with a cost, right? And that is what is important in this question. Why write the preconditions and algorithm? Algorithm, though, you will see from here. What about the preconditions? Precondition is this array has to be sorted. Most important precondition for binary search. The array must be sorted. The elements must be comparable. 12 must be comparable with 15. You cannot have here 12. You cannot have here A. They are non-comparable elements. So you should have the elements comparable. And it must allow a random access. That means I can go to here by saying ARR 0, or I can directly jump here by saying ARR 7, because that's what I will be doing. I'll be dividing, right? So I need not always go sequentially like linear search. I will be jumping. I will be halving the array. I will be going to a different dimension in a different index, right? I will go to the right side, then might go to the left side. So it's up to me what I want to do. So the data structure should allow me to do that. Array allows you to do that. These are the three preconditions of binary search. Very important for you to remember. Algorithm is also important equally, and the preconditions typically you tend to skip it, which is why I'm saying it is important. So that's on the binary search. Once binary search is done, they will also ask you this question: write an algorithm of binary search, calculate the time and space complexities. Right. So to calculate time and space complexity, it's going to be again simple. If you convert this binary search, this thing into a binary search tree, BST, you know about BSTs by now. So if you convert it into a BST, you will see that the entire left-hand side of this 27 is all less than 27 elements. All of these are less than 27. And all the right sides are greater than 27. Every node, let's take this node. Left side is less than 18. Right side is greater than 18. This left side is less than 41. Right side is greater than 41, and so on and so forth. Every element is like that. You have arranged the binary search tree or a binary tree in such a manner that this is how it looks like. If this is how it looks like, it becomes a binary search tree. Right? So if this is a binary search tree, then this is what is basically representing this particular array. Why? Because at every instance, we are actually taking a half of this. So if you are searching for 27, first midpoint is this. Second midpoint will be 18. In fact, second midpoint will be 18 on this side and 41 on this side. So 41 will be the second midpoint. The third midpoint will be 36. So we will take 36 as the midpoint. So within this array, 36 will be the midpoint. So we are slowly reducing the array, as you know about the binary search algorithm. Otherwise, please read it. Have a look at the lecture that I posted on YouTube also on binary search. You will understand. What I'm trying to say is this binary search is a representation of how this particular thing looks like. So when I say that, how does binary search work? Please explain through this diagram, right? What you will say is, suppose I'm searching for 39. Then I will first go here. Here I see it is 27. And I know in a binary search tree, the right side element will be greater. 39 is greater than 27. So I will go on this right side to search for 39. I will not consider this left side at all. And that is what you also do in the algorithm of binary search. You don't consider the left side. You actually move the left to the mid plus 1. Right? So that's where what you do is that. And then with this, you actually come in this side of the array. Then you say that 41 I get. 39 is less than 41. I will concentrate on the left side of 41. Then I will go to 36. But 39 is greater than 36. I will concentrate on the right side of 36. And in this way, I will find out 39. How many times did you search? First, second, third, fourth. 4 times you search, which is E. right? So when the 39, if I was searching for 27, then I would have found it here itself. That's my best case. So what is my best case? Best case is, of course, order of 1. Because I'm searching for 27, I got it here itself. What is my worst case? My worst case is I will get the elements here, because here all these elements are actually going to be searched in a search complexity of 4 times, right? So the 4 times is what? 4 levels for n is 15. N is equal to 15 here. See, n is equal to 15 here, right? So 4 levels because of 15 elements. If there were more than 15 elements, 4 would have been greater. So 4 levels for 15 elements, which is approximately equal to, I can say 15 can be approximated as 16 from a calculation perspective, implying that t, the time taken, is 4 for n equal to 16. So time taken is 4 for n equal to 16 means, can I put a relationship between t and n? I can put it like this: 2 to the power 4 equal to 16, which means that log equal to log of 16. What is t? 4. Isn't log base 2 of 16 4? That's what we found out here. So t is nothing but log base 2 of 16. What is 16? 16 is n. Therefore, Tn is order of log base 2 of n. So that is how your worst case is coming as order of log base 2 of n. If you get 4 to 16 correlation is a logarithmic correlation, right? So that's why you are getting T as log base 2 of n. And in the average case, if you see, again, we will take each element search. We will take each element search, and each element, if found, we will add their time complexities and divide it by 16, right? So what we have done, we are saying that assuming each node to be matched, level 1 has 1 comparison. I will just make a comparison, 1 search, right? 1 comparison I will do to check whether this is 27. Level 2, I will do 2 comparisons, 1 at level 1, 1 at level 2 to reach 18. So to reach 18, I have to check 27 first. Then I have to check 18, that yes, I have reached 18. So I have done 2 comparisons. Similarly, 41 also I have to do 2 comparisons. 27 first comparison and then 41 second comparison. So in the second level, I will be doing 2 cross 2 comparisons. So 2 comparisons for 2 nodes. There are 2 nodes here. So I get 4 from here. I get 1 from here. And then I will get 12 from here. Why? Because this will give me 3 comparisons, 3 comparisons, 3 comparisons, 3 comparisons. So I will get 12 from here. And the last one will give me 32. Why? Because this will give me 4, 4, 4, 4, and so. So shouldn't I write this as this? How many comparisons? 49 comparisons. 49 comparisons will be taken. What? 15. For 15, I'm getting 49, which is 3.2. 3.2 ceiling is 4. So 4 implies what? Again, 4 implies log base 2 of 16. 4 comparisons, worst case, average case scenario is coming. But this average case 4 comparison has to be converted in terms of n. And that's why I'm converting it in terms of n, saying that log base 2 of 16 is nothing but log base 2 of n. So that is my binary search. So there are 2 questions on binary search, one on the preconditions and the algorithm, and another on the time complexity of binary search. And of course, this question is equally important. Whatever you learned in binary and linear just now, put it as a difference. So precondition is there in linear? No. But in binary, it is there. It is scanning elements sequentially, but it is doing a divide and conquer. Here, already you have learned what is the best case, average case, space. Here also, you know what is the best case, average case, space. That's all. And I already told you that linear search cannot be used for larger data sets because its complexity is order of n. So you go for binary search for larger data sets. So that is what the comparison between linear and binary search is all about. With that, we come to the end of the first section. Let me check your comments. Come with your comments. I will go from the top and see if I missed out. If you have comments, please start your comments on whatever we have discussed. Okay, minimum heap is not there. At least from a TINT search standpoint, minimum and maximum heap is not there. I only see these things. Anybody else has any questions? Yeah, I don't see any more questions. Any other question, guys? Otherwise, I'll move on to the next topic. Because I can't hear you. If you are communicative on the chat, it helps. Can you just type move on? Then I can move on. I can assume you can hear me. Yeah, chalo, next topic. Okay, asymptotic notation. Quickly, we will finish this off. Asymptotic notation says that I have these many notations to cover. Let's say all of you are aware in asymptotic notations that there are some standard notations from a complexity standpoint, time complexity or space complexity standpoint, right? So those standard notations say that I will have a standard notation for constant, which we already know, order of 1. There is an order of log n, there is an order of n log n, and so on and so forth, right? And this goes on in this order in terms of the time, right? The more you go on the left side, the more your order of complexities increase, more the time increases. Now, this particular equation, right, it is so easy to tell the complexity. If from my algorithm, I get 6 as unit of time it is taking in a particular machine, whatever machine, don't worry about that. If 6 units of time it is taking on a particular machine, can I say that it is order of 1? Of course, I can say we just now saw that this is an order of 1 because it will take 6 units in my machine. It might take 2 units in some other machine, but it will not change with the input. It will always take 2 units in that machine, 6 units in my machine, right? So I can, of course, say that this is an order of 1. Can I say 3n plus 6 is an order of n? Y equal to mx plus c, I can say that. So this becomes order of n. Can I say this is a quadratic order, which means it is an order of n square? I told you, right? Take the highest degree of n as the order. So highest degree of n is order of n square. So all of these we can definitely classify amongst any one of these standard complexities. But life is not that simple, right? What will you do for this? You cannot classify this against any one of those lines. So this line will actually look like this, right? So this line will be this Tn line, this Tn line, right? Now, what do you say for this? You don't have any standard complexity to talk, and your algorithm has produced this. Then to the external people, what will you say? What is your order? They will say, I'm going to take your algorithm, I'm going to buy your algorithm. What is your order? You can't answer, right? So which is why you have these asymptotic notations, which says that I don't know the order, say that it is not going to go above order of n, right? So this is my upper bound, that is big O, and it is not going to go below order of O log n, which is my lower bound, which is going to be your omega, and its tight bound will be theta, which I don't know. Tight bound is the actual order. You don't know that, right? So theta you don't know, but you know that it will not cross O and it will not go below omega. That's what you will tell to the person who is buying it from you. So that is where your asymptotic notation is helping you. When you don't know your theta, then you can ask for a big O or omega. And that is what asymptotic notation is all about. Now, if that is understandable, then what is big O? Big O is basically where you see that if this is a function, cgn1n cube, and this is also a function which is 1000 n square, then at a particular point on the graph, by the way, this is time versus n, the same graph that we saw, right? An algorithm, right? So that, let's say the algorithm is taking this amount of time. If the algorithm is taking this amount of time, can there be a graph? This algorithm is what? This yellow line. So this yellow line is taking a quadratic order. So can there be a line which will be higher than this line at a value of n? If there is a line which is higher than this line at a value of n, then that line is called as, that line's gn, like that line's gn is going to be called as big O of that particular. So I will say that big O, what is cgn is equal to 1 n cube? That means c is equal to 1 and gn equal to n cube. right? So that is what its meaning is. So I can say then that this particular function, because this line has gone above it, so it is representing an upper bound. It is representing an upper bound of this particular line, right? So I can therefore say that the function n, the upper bound of this function n, will be the upper bound of big O of Gn. Because Cgn is 1n cube, which is above it, I will take help of Gn to say that you are my upper bound. And what is that going to translate to? Upper bound of n cube. So I can say that 1000 n squares upper bound is big O of n cube. Right? So that's what big O notation is actually talking about. So this is how you will actually get a question also, that if this particular Cgn, right? If there is a line that is Cgn and it crosses above Fn, then does it represent omega? Does it represent big O? Does it represent theta? Right? So you have to say that because it is above, it represents an upper bound. Upper bound is omega. Big O, right? And omega is here. Below is omega, right? So if your algorithm is producing Fn equal to 2n and your Cgn is 1n cube, right? Can I say that at a value of n0, this line will always be below my algorithm's time complexity? If this line is always below my algorithm's time complexity at a value of n0, then this line is the lower bound. If this line is the lower bound, this represents omega of Gn. Right? So omega, not omega of Gn, sorry. This line will represent the time complexity will be omega, which will be equal to, yes, omega of, I was right, omega of Gn. Now Gn is what here? See, Gn here is also n cube. So this will be omega of n cube. Right? So that is going to be my time complexity in terms of my omega. Right? So my omega will be, my Tn will be omega of n cube, which is the lower bound time complexity for my function Fn equal to 2n. So here also the same set of question can come, saying that if Cgn is less than your Fn, then what does it signify? Does it signify big O, omega, or theta? It signifies, Cgn signifies what? Omega, because it's a lower bound. Right? So that's on that particular part. Then on the theta, which is a tight bound, it's basically saying that at a particular value of n, my Cgn will cross, at a particular value of n, my Cgn will cross my Fn. Fn is my algorithm's complexity. There will be a line which will cross this particular line at a particular value of n, and there will be a line which is also going to be below this particular line. So there are two lines here we are talking about, one line which has crossed, one line which is below. And in both these two lines, you will see that Gn is going to be constant. Only thing that will change in these two lines are the C1s and C2s, right? So these C1s and C2s will change, Gn will be constant. Then only we can say that we have Fn is being tightly bound by we can say that Fn is equal to, the time complexity of Fn is equal to theta of Gn. That is the tight bound of Gn. So we can say theta of n, because Gn is nothing but our n, right? Here also n, here also n. So Gn is n in both the lines. Both the lines Gn has to be same, that's why. Right? So we will say that when such a thing happens, then I can say theta, the time complexity that is tight bound, is equal to theta of n. Why? Because Gn is n in this case. So that is theta, which represents the tight bound complexity, the actual time complexity of that particular line, not the upper bound, not the lower bound. Right? So what typical questions come? Is tight lower bound same as tight bound? Tight lower bound. Anything tight is tight. Lower bound, upper bound does not matter. Anything tight means it is average bound. It is the actual time complexity. It is not lower or upper. Tight or average bound is the same. So tight lower bound is denoted by theta, right? Tight means theta. You put lower, upper, does not matter. Tight will supersede. Remember that. Now see, I was saying some question like this can come. Which notation comprises a set of functions Hn? Right? It's saying that which notation comprises a set of functions Hn that are greater than or equal to Cgn for all values of n greater than n naught. So Hn, my algorithm's function, is greater than the graph. Hn is greater than the graph. That means my algorithms, below my algorithm, some other graph is there. So if my algorithms below something is there, this is lower bound. This line is lower bound. Lower bound is represented by omega. So which notation? Omega. Right? So that is the answer to this question. So that was on asymptotic. Right? Now come to my comments. Partho is asking, CA3 will be code-based or theory? We are discussing everything that may come on CA3, Partho. So go through the lecture. You will understand. Right now, as I said, nothing will be code-based. Everything will be algorithm-based. Theory will be there. Algorithms will also be there. Right? So everything okay? Am I audible? Are you able to see the screen? Just say okay so that I can move on to the next topic. Okay, fine. Thanks for responding. Be responsive on chat because I can't hear you. I can't see you. It's very, very difficult to do a session like this. So be with me. Stacks. We are getting into stacks and let's do a time check. We are at 2:52 and I said I will finish off by 3:30 stacks. So I have half an hour to finish off stacks, but I think I will be done before that. So ADT and operations, very important from a semester as well as CA3 standpoint. What is an ADT? Because what is an ADT? This is a new term for you. So of course, it becomes very important to actually ask you about this new term. So what is an ADT? As I said in my lectures, ADT is about getting to you a data structure. You use the data structure. You don't have to understand how the data structure works. You don't have to understand how a pop works in a stack. Use stack. I have given you stack. Use stack. Use the pop of stack. Use the push of stack. You don't need to write the code of push and pop. I have written it for you. You use it. Right? So that is what is abstraction. And any data type that actually has that abstraction is called abstract data type. So that's on the abstract data type. So it hides the implementation details and therefore it is abstracted. The implementation is abstracted out. ADT tells us what it does, not how it is done. Right? So we will not understand how it is done. We will just see what is being done and we'll use that what. Right? Examples are stack, queue, tree, anything that gives you operations. Those operations are your abstract methods, right? Which is what we are trying to use. So that is what is ADT. Now, all of you are doing a lot of ADTs. You have done stack, linear queue, circular queue, Deque, linked list, double linked list. All of you have done it. And all of you are probably getting a bit confused as to some has push pop, some has NQ DQ, some has insert at beginning, some had insert at position. How to make a method of this madness? I've tried to put a table here just so that you know. All the ADTs will have these 5 things. All these ADTs will have these 5 things. There will be an insert. So stacks insert is called what? Push. Linear queues insert is called NQ. Circular queue insert is also called NQ. Right? DQ is 2 times. Insert is 2 times because it can be at the front of the queue, at the rear of the queue. So there are 2 inserts. Linked list. Linked list, we can insert it either at the front, at the rear, or in between. And double linked list also, we can do the same. We can insert it at the front, rear, or at the at any particular position. So when I say insert, this insert will translate to so many things across the different ADTs. So you have to remember that each ADT gives you an insert operation, right? Push, NQ, NQ, insert front, insert rear, all of this you will have to resonate from the type of the ADT. That okay, acha, insert is there, but how many inserts? Insert front, insert rear, yes, because it's a DQ, let's say. Insert front, insert rear, yes, because it's a linked list. Additionally, it also has insert at a particular position. Similarly, for delete, you will have pop, DQ, DQ, delete front, delete rear for DQ, delete at beginning end position, delete at beginning end position. So all of these are deletes only. So then you will not forget that, okay, the second category is everything should have a delete. Next is everybody should have a peak. And peak will happen from where? Peak will always happen from the position where it goes out. So where does it go out from? Top. So sometimes it is called peak in a stack. Sometimes it is also called top, right? Sometimes. And because you already maintain a top pointer, typically it is not called a top method. It is called peak. Next, a linear queue also has a peak. From a linear queue, where does it go out? From the front. So front could also be the method name. But front, again, we maintain a pointer. That's why we will call it as peak. So every ADT will have a peak. Because DQ has two areas from which it can go out. As I said, peak is what? To consider the areas from where you go out, just try to visualize the element there without pulling them out from that particular area, right? So that's what we are trying to do in peak. So in DQ, we have two areas where it can go out, one front, one rear, right? So therefore, we will say peak front, peak rear, right? So for DQ. For linked list, there is no peak. You actually can do a get. There is a get functionality with which you can get any element, an ith element, right? In fact, for double linked list also, you have that get method. So there is no restriction in a linked list, which is why you are allowed to actually check any element from a peak perspective. All of these ADTs will have these two functions, except for linked list. All of these will have check full, check empty. Of course, we need to do both of that. Is full or is empty? We have to check all of them. All of them will have that, right? So that's what it means from an ADT. I just wanted to give you a view of what all ADTs you have and what all functions those ADTs or operations those ADTs will have, how to quickly remember those functions, or how to quickly create a method to this madness across so many functions, how to remember. I'm saying that just remember 5 categories, and then each of these categories, you don't even need to remember. Position that category against the ADT, you will understand how many functions are there for that category. Insert, definitely for a linked list, you will know that linked list will allow insert at beginning, insert at end, insert at middle, right? So that's all. That's how you need to remember. Now, if we get into stack operations, then in stack operations, we have these algorithms, which is your push, pop, peak, full, and empty, right? So I will again not go through the algorithms. This algorithm is a question. If you see, write the algorithm for the standard operations of a stack, right? And this is how the algorithms need to be written. Peak and pop, if you see, the only difference is pop will adjust the top, peak will not adjust the top. Peak will just return the stack at the top. Peak will just return the stack at the top, but it will not adjust the top, so that the top doesn't move, which means the element is still there. That is what is peak. So the operations are here, the algorithms are here for you to have a read. Yes, so the application of stack here is important. Define recursion. What is recursion? Recursion is a repetitive step of calling the same function over and over again, right? So as to achieve a larger set of work. So smaller set of inputs to achieve a larger set of work is what recursion achieves. If you remember the factorial program, this is your favorite factorial program. This is how it looks like. There is a main, there is a factorial here, and this factorial function is the same factorial function that you know about. Now, let us say that the question is that, okay, define recursion, but also explain how stack is being used in this entire recursive program. I have not used stack here. There is no push, pop, etc. So why this question? So internally, the computer will always, or the compiler will always use a stack when there is a function call like this, right? If you do a int main, right, from within int main, you are calling another function. So main says that in order to execute, I need two things. One is I need to store my parameters somewhere. What is my parameter? Right now, there is no parameter, right? But it could have a parameter. If you do a character argument to take command line arguments, you can actually take main as a parameter also. Or it will also say that whatever are the local variables that I am using, what are the local variables it is using? Let's say int n equal to 3 it is using. That's a local variable. It will say to the compiler that I need space to store this. Compiler will say, come to stack. Come to me. I will take you to Mr. Memory, which is actually arranged in the form of a stack. And I will give you this bottom slot, right? And in this bottom slot, I'm getting a call, so you might be hearing it, but I will not pick it up. Let's continue. So I'm getting so I'll put you into this stack, and you use this stack for your parameters. You use this stack for your local variables, right? You have local variable v1, v2, v3, right? Use it, whatever. So this is main, right? This is what main will want from a memory standpoint, which starts to execute. So main will come inside here and say, I want this memory, and I will execute myself using this memory as my help. And it starts executing. It goes to this line, it goes to this line. As soon as it goes to this line, you see there is a function call, right? You see there is a function call here. So if there is a function call here, main will have to let go of the control, because the control will now move to another function. Main is a function. This is also a function, right? Both of them are functions. So the control will move to that function. So main will say that, okay, you are asking me to release control to factorial. What happens to my memory? Because I'm not done. I have to do this, 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 this. I am not done, right? So how will I store this? Compiler says, keep it there. Compiler says, keep your memory here and make a call to the factorial function. This memory is safe with you. I am not going to touch it, right? So this memory therefore becomes main's memory, and it makes a call to factorial of n in this case is 3, right? So main makes a call to factorial of n. As soon as that happens, this factorial function will come into the scene. This factorial function will also say, I need this as my, I need this for this parameter to be stored somewhere. I need local variables to be stored somewhere. So then compiler will say, come to me. I will give you that space. So compiler says that come. So factorial goes here. Factorial 3, right? Comes here and takes this particular stack space and says that I'm going to utilize this stack space. Compiler says you are perfectly allowed. Please go ahead and do it. Now factorial sees that it has to call factorial n-1. So factorial says that I have to call another version of myself, but it's a different version, right? I mean, it's a different person, let's say. It's a different person, meaning it's a different function. It's not my function. My function is here. I need to call another version of the same function. And that same function, before calling, it says that I know that I have to do. So it says that I'm going to do this. I'm going to do 3 star something I have to do, right? And that something I don't know, I'll have to call a function. And that function becomes factorial 2, right? So this factorial 2 will then say, I need memory. So it will come inside this stack. And this will go on. So it will say that I know I need to do 2 star some amount, something will come, which I don't know, for which I have to call another factorial, which is factorial of 1. Factorial of 1 means it's a base case. It will. So therefore, this factorial will say that I am done. I will return 1. So that return will go here. As soon as that return goes here, this particular stack will become empty, which means top will move here. Then this input that came from factorial 1 will be calculated 2 into 1. 2 into 1 will go here, which is 2, right? So it will go here, and this will become empty. That means my top will therefore move here. And this 3 into 2 will therefore now become as 6, and this will return here as 6. And this particular memory will be freed, and this top will go here. And then main will execute all of these lines, and it will finally output 6 as the output. And then this will also be released, and top will be at -1. So that is what happens on a stack perspective. For a recursion, it happens for every function. Forget about recursion. It happens for every function. Every function needs to store itself when it calls another function. Right? So that's what is happening as I explained here. And that's what this question was. Explain the usage of stack. The usage of stack. Whatever I explained, you have to explain in your own English. Write this in this manner and explain in your own language whatever is explained here. So that's on the application of stack. We will get into some precedence calculations. So let's understand this table. Just from a recap perspective, brackets have highest precedence. You have a dollar, sometimes you will see, which is basically a exponent sign, which has again a higher precedence. Then star, slash, or modulo. Star, slash, or modulo has the same precedence. So precedence is this. Precedence is this, which actually classifies who will go first in this order. But if you have the same operators here, then who will go first? That is associativity. So right to left or left to right associativity. That is what associativity means, and that is what precedence means. So a lot of people don't know what is precedence, what is associativity. This is what is precedence and associativity. Now you know about this, so I'll move forward here. This question is very important, which says that infix to postfix, what is the algorithm? Right, so this is the algorithm. Now, you don't need to remember all of this. If you understand the process of conversion of this using a stack, right? Of course, always use stack to do this. Do not use algebraic method. Algebraic method will never be asked that do algebraically. It has never been asked. It will not be asked. Either they will not say anything that convert infix to postfix. Just they will say that. You can use stack. You can use algebraic. But if they have said convert infix to postfix using stack, then what will you do? If you have just done algebraic, you will not be able to solve it, which is why I'm saying for both the cases, treat it as to be done through stacks. And this is the algorithm for doing it through stacks. Don't worry about all of this English. I'm assuming if you understand the process, you can write this English. Let us see the process. The process is that if you get 9, what is 9? 9 is an operator, right? When you get an operator, put it into the output. Write this sentence as an algorithm. If we get an operator, we will print it in the output, step 1. That is as easy as that. If you understand this logic, you can actually write this like that. Then we will say that we have got plus, right? We'll go left to right, we'll get the next expression, which is plus. This is not an operator. So if it is an operator, then put it at the output. If it is not an operator and it is an operand, sorry, I was taking operator and operand interchangeably. We had got an operand here, and that operand will go to the output. And this is an operator, so it will not go to the output. It will go inside the stack. Right. Next, you have got an operand, so it will go to the output. Next, you have got a star. This is an operator. Now, it will go into the stack provided its precedence is greater than plus. Provided its precedence is greater than the top of the stack. So, when it was entering here, what was there? Plus. So, is star greater than plus? Yes. So, it will become the new top of the stack. Perfect. Now, let us go. 5, it will go to the output. Minus, so minus needs to go here, but minus can't go here because the top of the stack is right now here. So the top of the stack is having star. Minus is not greater than star in terms of precedence. Therefore, minus will want star to go out. So star will need to be popped. So star will be popped to the output. Right, star is popped to the output. Then we have minus. It can come in at this place, but can it come in at this place? It cannot. Why? Because if I put minus here, then niche we have plus, right? This minus has to be greater than plus, not greater than equal to. Minus and plus have the same precedence. So minus wants plus to move out. So plus will also move out. And now minus can come here. So that is what minus will do. That minus will now come here because the stack is empty. So it is perfectly fine to actually come in here. Next, we have bracket, and this bracket will need to be pushed into the stack blindly. The starting bracket push into the stack blindly. Right. Next, we have 3. 3 will go to the output because it is an operand. Plus will go here. Bracket is considered to be least priority. Unlike the precedence table, this is an exception. When inside a stack for infix to postfix conversion, bracket is considered to be the least priority. So plus can definitely go above bracket because bracket is least priority. Then we have 17, and this 17 will be an operand which will move into the output. Then we have the ending bracket. When you encounter an ending bracket, then you will pop everything till you get the starting bracket. So this will be popped, this will be popped. This plus that is popped is written here, and this bracket that is popped is discarded. So we are done with this bracket also. Next, you have a star. Star can go here because you have minus below it. Minus is less than star. And then we have 5. 5 comes here, and then we have the string is over. So pop everything out. So the star gets popped first, written first. Then the minus gets popped, written here. So this is what is the infix to postfix conversion. Whatever we did, whatever logic we applied is written here. You don't need to read it. If you read it, you will understand. But I am saying that don't try to remember this. Whatever you understood, try to write in your own language. That is infix to postfix algorithm. If you don't want to do it in this writing manner, in this visual manner, right, you can also do it using a table. Right, so this table you can see, or this table. So I've given 2 more sums. This one also has 1 sum, infix to postfix, and I've given another sum also. This one, which has 2 brackets. So it is, if you do this sum, I think you can do any sum. So I would prefer you practice this sum very well. Right, so because there is 2 sets of brackets here. And this is how the stack looks like. I'll just take you through 1 or 2 steps. I'll not go through the entire thing, just to make sure you understand how this table is written. What you are getting stack has nothing, empty. Then minus comes in. Minus will get into the stack. So there will be a push operation into the stack. And the output still has A. Right? In this way, it will go on. So now you can understand and correlate with the visual stack that we drew in the last slide versus this. There is no difference. It's just that we are writing it in a table fashion. All these are getting into the stack, and then the pop starts happening. Right? And this is how, when the pop starts happening, the output starts increasing. And this is your final output. Right? So that's what this particular sum. So practice these 3 sums in order to infix to postfix conversion. This one, which doesn't have a bracket, but remember this has a $, right? So which means it is a exponent. So you have to put the exponent's precedence highest. Accordingly, you'll have to do this. And this one, because it has multiple brackets. Now we have done infix to postfix, but now that we have a postfix, we'll also have to evaluate the postfix using stack. Again, this is an algorithm for that. You don't need to remember it. If you remember the process that we'll explain just now, I think you can very well write this algorithm. Process is, you are given this string. This is your postfix. You are asked to evaluate this postfix. So what you'll do, take the operand, push it into the stack. 16, push it into the stack. 2, push it into the stack. Plus, it's an operator. So put plus here. Pop 2, put it here. Pop 16, put it here. The first pop, put it on the right side. The second pop, put it on the left side. This is for the second pop. This is for the first pop. Remember this sequence, otherwise your sum will be wrong. 16 plus 2 is 18. This 18, push it into the stack. So this plus is done. Then you have a star. So to do this star, again you'll have to push 18, put it here, right side. Then you are doing what? A star, and then 3, put it here. This will be 54. So put 54 here. 3 3s are 24. 2, 3, 54. Fine. So 54 we will put it here. Then we will have 12. This 12 will go here. Then we will have 6. This 6 will go here. Then we will have slash. So for slash, we will say 6 will be popped. 12 will be popped. So we will get 2. 2 we will put here. And that 2 we will have to apply minus. So minus means 2 will come out. 54 will come out. Minus will be in between. And that is your answer. Right, so this is the process. You will push the operands into the stack. Whenever you get an operator, you will take the first pop in the right side, operator, and operand again. And then evaluate it, put it back into the stack, and keep on doing it till the stack is empty. And you get your expression. That is what you have to write under the postfix evaluation. Same thing, if you don't want to do it using that stack diagram, you can do it using this same table. It is in the same way. I'm not explaining this same way as I explained the other table. But again, from a question perspective, let me see if it's the same question. No, it's not the same question. So this is a different question, different value, and this is a different value. If you want to practice both, please practice both. Now, prefix to postfix, we have understood infix to postfix, and we have also understood postfix evaluation. But prefix to postfix is kind of different. The only difference in prefix to postfix, see, this is a prefix expression, right? And this prefix expression, that's why this is important, because it's not coming under a standard operation, right? So that's why this becomes important, that how will you convert a prefix to a postfix? So stars plus AB minus CD. It's a simple expression, but because it is prefix to postfix, please understand the process. The process is, instead of going left to right, you'll have to read it from right to left. And then the process is the same. Then the process is the same as what we did here. So let's go to the process. What are we doing? This one. If you remember here, what we did, the operands we were pushing into the stack, and the operator, when it comes, we were evaluating it. Here also we'll do the same thing. See, we got an operand. We are now treating it from right to left. The right to left means what? DC minus BA plus star. So when it comes to prefix to postfix, you will have to first say that I'm going to reverse the string and then start doing the pushing into the stack. So first thing I get is D. So D is a operand. Operand means it should go into the stack. So stack will have this. Next we have C. C is also an operand. So it will be pushed into the stack. Stack will have this. Remember, this is your top. The last item is your top of the stack. Right, now we have minus coming in. So when we have minus coming in, then our job is to actually do an operation from this particular element. So we will pop C. We will pop C and D. And we will form CD minus. So basically, this C will be popped first. This D will be popped first. Next. So C, D, and then we will say, we will do a minus of all of that. Right? So that's what we will say when we say that we will do CD pop with a minus. So this minus is actually helping me to pop out C and D and create an expression which is CD minus, and this CD minus will now move into the stack. Because we are creating a postfix expression, I am not putting this minus in between unlike my infix evaluation, right? So I'm going to say that CD minus because we are doing a postfix evaluation. And why C first? Because C was the top element. That's why I'll take C first. Then we have B coming in. So this B will go where? This B will get into the stack, right? And by the way, the CD minus that you got, you were supposed to push it back into the stack. That's just like our previous cases where we were evaluating, let's say 18, 52, right? We had pushed it back into the stack. Here also CD minus is an evaluation, right? So it will be pushed back into the stack. Then we have the operand here, CD minus B. We will push it into the stack. B operand, so it will be pushed into the stack. I think you can understand that. So this push happens. Then we have A, it will be pushed into the stack. Then we have plus. So plus means 2 will come out. So A will come out, B will come out. Because we are working with postfix, this plus will go there. Now this entire thing will be pushed back into the stack. So we now have CD minus and AB plus. Right? Now we have star. So CD minus is one term, don't forget it, and AB plus is one term. Because it was C and D, you could not evaluate it. Suppose it was numbers, you could have evaluated it and you could have put one single number. So we are assuming that this is one single number, this is one single number. So both the numbers will be popped, right? Both the numbers will be popped. The first number is AB plus, and the second number is CD minus. And on top of that, we will say star because we are evaluating star. So we are doing the postfix. This is one number, this is one more number, and we are doing a postfix on that particular number, and then we are pushing it back into the stack. So this is my final postfix expression. Because then this string is exhausted, nothing more to do. So this becomes my final postfix expression. So that is prefix to postfix. This is important because this is kind of tricky, different. That's why it's important. Time complexity, I hope you will understand, because every time an operator is coming, operand is coming, it has to be pushed. So it's going to be order of n. All of the inputs of the expression, right? If an expression is x plus y minus z, this is one character. This is one character to be processed. This is one character, one character, one character. So if I take an array and put array, right, I'll have to process n elements of this array. That is, total number of elements here is what I need to process. That means my time complexity will be an order of the number of elements. So that is why the time complexity of infix to postfix will be always order of n. The reasoning is here. Please check the reasoning when you are reading this. Reverse Polish notation is known as postfix, and Polish notation is known as prefix. So that's all there is to it. RPN, people call it as RPN. In your exam, RPN can also be abbreviated. Don't get confused. RPN means reverse Polish notation, and which means postfix. So that was on stacks. Let us see your comments. Imagine there is a drawing application. There is a application with draw lines, curves, add shapes. You could also undo the last action and undo backwards. Which data structure? Achha, okay. Imagine there is a drawing application with drawing lines, curves, and add shapes. You could also undo the last action and undo backwards. So what are you doing? You are popping out, na? You are popping out the last action, whatever that last action is. So which data structure we are using? We are using stack, right? Whether you will get a question like that or not, I can't say, but it's a good question. You will get into stacks for that, right? So that's where we will say that this is actually a stack which will take each and every line input inside the stack, and whatever we drew, that basically x and y coordinate collection, it will take inside the stack. And if we are undoing it, that x and y collection is at the top of the stack, we will pop it out. That pop will be the undo of the last action. So that's basically a stack that we are trying to use here. We could use a stack. Whether the question will come, as I said, I cannot comment on that, but it's an interesting, good question. No other questions. Otherwise, we are bang on time. I said 1 hour 30 minutes, and we have finished half of what we wanted to cover in 1 hour 30 minutes. Can you just confirm that everything is okay? We can move forward. Anyone? Can you confirm? Can we move forward? Okay. Fine. Now let's move on. We are talking about linear, circular, and double-ended queue. We will try to finish this in half hour so that we are at, when did we start? 4 o'clock, 4 o'clock. Yeah, we'll finish it off by 4 o'clock. Now, linear queue is looking like this. In a queue, all of you are aware that a queue, the exit will happen from here. The entry will happen from here. This is called the front of the queue. This is called the rear of the queue. Right? So this is front and this is rear. Right? Now, when we say that what is important in linear queue, the operations are important in linear queue. Their algorithms are important from what we have listed out here. So this is what is important, right? So please remember these algorithms. Remember that a queue exits from the front and entries from the rear, and you have a front and rear pointer. I'm not going to go through the algorithms again. As I said, you will refer to my video lectures to go through the algorithm. Otherwise, this class will easily go for 6 hours. What you need to understand is that if you have a queue where, let's say, you had the first push of 20. Let's do this, right? Let's do this 20 push, NQ. So 20 will come here. Let's do another 4. 4 will come here. 41, it will come here. 67 will come here. And then 5 will come here. So where is my front and where is my rear? Right? So let's figure that out. My front pointer is going to be here. My rear pointer is going to be here. Now my queue is full, right? If my queue is full, after this particular step, do a DQ, then this particular element will move out. Actually, this element doesn't move out. What happens is front moves forward. This element is still there, but for all practical purposes, we will consider it is not there, right? So this front moves forward. Again, we do a DQ. Then this front will also move forward. Again, we'll do a DQ. This front will also move forward. And again, we'll do a DQ. This front will also move forward. Now, that means front is right now here. All these elements are not there. And we just have front and rear pointing to the same location. That means we have a single item in the queue, which is 5. Now, can I insert any more items? Can I NQ an item? I can't, because NQ wants rear to be ++. And rear cannot be ++ because it will go out of the bounds. Therefore, I cannot NQ any more items. But don't you see free spaces here? So that's the problem with linear queues. That because front is moving forward and it can never go backwards, these spaces are lost. And that's what I have written here, that this is a wastage of memory. And we have a limited number of insertions, because I know that I can only insert 5 inserts. See, after 5 inserts, I cannot insert anymore. There is a limited number of insertions. So these two are the disadvantages of linear queue. Please remember these disadvantages very carefully. Next, circular queue. Now, circular queue takes care of those disadvantages. It says that my front can be here and my rear starts moving like this. And if my rear comes here, suppose rear comes here, then comes here, then comes here, then comes here, right? Somewhere it is, sometimes it is here. And in such situation, let's say front is here. Now, in this case, if my front and rear are looking like this, and I NQ one more item, right? So what will happen in this situation? When I enqueue one more item like this, in fact, before enqueuing, what I'll do is I will also do one more this one DQ. So let me do a DQ. So the DQ will take my front from here to here, right? So my front, because I DQ'd, front will have to move forward. Therefore, front moves forward. My rear is here. So now I have this position as free, right? And I'm now going to do an NQ. So if I do an NQ, right, my rear has to move forward, means 4 has to go to 0. So how will 4 go to 0? Rear cannot go to 0 because we are doing rear plus plus. 4 will become 5, and there is no index called 5. So 5 has to be converted to 0. How do we do that? We do a 5 modulo from a linear cube. Suppose you know these are the algorithms of a linear cube, right? Suppose you know these algorithms. Coming to a circular cube, you will remember this screen, which says that for the NQ process, this is my linear queue algorithm, and this is my circular queue algorithm. What is different? This rare plus plus was happening. Here, rare plus plus will actually take it to 5. So I need to do an adjustment here, and that's all that you need to do in a circular queue NQ. Similarly, for DQ, when we were doing a DQ, front was going here. Suppose front went here. Suppose front went here. Then suppose front went here. Then suppose front went here. Now rear is not here. Rear is, let's say, here. So rear is pointing here. And again, you might be listening to a phone call. I apologize for that. You should have put it on silent. Forgot to do that. But not touching because the camera is coming from that mobile only. Okay, now the rear is here, the front is here. So in this case, rather I took it as a reverse case. Reverse case is actually happening here. Suppose front is here, rear is here. This is perfectly possible because front DQ will move forward, right? So that's why front will come here, right? And then rear will actually follow suit. So the queue is going like this, right? This is my front, this is my rear. Now, if I do a DQ of this front, right, the front will have to move forward. If I do a DQ, then front will have to exit, right? Element at front will exit, and the count would move forward. Front should move forward. So front should go here. So if front goes there, right, what will happen to your 4? 4 will again go to 5. So either front is getting increased here, where here, see, this was where in the linear queue front was getting increased. This was in the linear queue where rear was getting increased. So either for an NQ rear will increase, or for a DQ front will increase. But both increases can happen from 4. If both increases happen from 4, I should have a situation to handle 4 going to 5, and that 5 to be converted to 0. And that is why I will do this here, I will do this here. So those are the only changes that you need to do from a linear queue to circular queue standpoint, right? And then because that can be done, the fullness of the circular queue is supposed to happen from saying that, let's say my front is here, my rear is here, right? Can I and I have all the elements here, right? So I have an element here, 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 right? So I have all the elements here. So my front and rear are here. Now, how will I say my queue is full? My queue is only full if by increasing my rear by 1, if increasing my rear by 1, I reach to front. You know that, right? You can see that here. If I increase rear by 1, I will reach front. And that's where I will say that my queue is full. There is nothing, no space in between. Everything is blocked here. Rear plus plus, any NQ will do what? Rear plus plus. Rear plus plus is moving rear to front. and that is where there is a problem. If rear goes to front, then rear plus plus should take it to 0. From 4, how can you become 0? Again, do the modulo. So that is the only difference between this and this. So this way, try to remember. Rest every syntax of linear queue remains the same as circular queue. Only area where you are doing a plus plus of rear, plus plus of front, please change it to the modulo. Empty remains the same. Right? So that's all from a circular queue standpoint. And of course, you can have the display. Display, I have not put it in the main function because the operations do not consider display as an operation. It is considered as a helper function. But you know how to do a display. So display algorithm can also come where you might be asked to display a queue. Right? So display a queue means what? You have to check the emptiness of the queue. If the queue is empty, what to display? Right? And then what you will do is you will take I as front because now you are going to move I. Right? What you will do is you will say I is front. So front is here. Let's say this becomes my I. And then what are you saying? I equal to rear. So rear is, let's say, here. So if my I goes from here to here to here to here and to here, then I have displayed all the items. Therefore, if I equal to rear, break. Otherwise, I will be increased, I will be increased, and I will display. But what happens if I is here and rear is somewhere else? It's a circular queue, right? It need not be like this always. It can be anywhere. So what happens if I is here and rear is here? So I has to move towards this, right? So then I plus plus will take 4 to 0. How? Again, do the same thing. I plus 1 modulo max. So that you move circularly. And once you are done in this loop, you will actually print the queue that is at the position of I. And that's your display function. So all you need to do is run a loop. You know how to run a loop in an array, but make sure that the loop does a circular loop. That is, make sure your modulo is in the correct place. That's all there is to this algorithm. So one interesting question, this I gave in the WhatsApp channel also. Right, a circular queue is implemented using an array of size 10. The array starts from start. Front is 6, rear is 9. If we draw this, right, if we draw this, then 2, 3, 4, 5, 6, 7, 8, 9, 10. So array size, the array starts with an index 0. Well, front is 6. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The array is at this, front is 6. So front is 6 means front is here, right? And rear is at 9. Rear is at 9. The insertion of the next element, when you do a insert, what is that? NQ. NQ changes what? Rear, not front. So rear has to move forward, right? And that's why intentionally they gave 9. See, size is 10. They gave 9 here, 1 less. That means they know that you will do a plus plus and you will go out. So what formula will you use? Same formula, na? This is the same formula you will use. So where will the next element take place? Rear plus 1. Rear plus 1 means 9 plus 1. Modulo size, which is 10 modulo 10, which is equal to 0. So the next element will be at 0. That's the answer. Now this 10 can be anything. This 10 can be 20, 30, 40. They can give you anything, 50, right? And this 9 will be intelligently, if it is 20, it will be 19. If it is 30, it will be 29. If it is this, it will be 39. If it is 50, it will be 49. You'll have to understand it's the same thing. It's at the last but one position, and therefore plus 1. It's actually at the last position of the index, and therefore plus 1 will actually take it to the outer bounds. So module. That's on this question. Other questions important from a circular queue is state the difference between stack and queue. So stack and queue difference, remember 4 things. 1, principle, which is the LIFO FIFO. Even if they ask you to define a stack or define a queue, remember these 4 things. First, the principle. Second, how does insertion happen? Third, how does deletion happen? Fourth, one application. And this you can apply to any ADT. This concept, this template of principle, insertion, deletion, application, you can apply to a definition of any ADT. Right? So this is one question which is important. Why circular queue is better than simple queue? You know the answer, because it helps to reduce that wastage, right? It reuses that free space. And you can do more and more NQs and DQs. You don't need to stop. Because you can reuse, you can do more and more NQs and DQs. No shifting needed after deletion. What does this mean? No shifting needed after deletion? Because when you are actually deleting some element from sometimes there is another version of a queue which you don't know. So all you know is that a rare goes here. That means my NQ, happens from here, and my DQ happens from here. This is what you know. And when you are doing a DQ, your front is moving forward like this, right? But if I say that that is not what happens in a physical queue, what happens in a physical queue? When this person is gone, DQ'd, then this person moves forward, and so on and so forth. So this entire line should move forward. That's not what is happening. We are moving the front backwards, right? So basically, that's what is happening on the front side. So we are moving the counter as if, not the persons. We are making the counter come to the next person. I hope you can understand what I'm saying. So that is what is creating a problem. So why can't we actually create something that is similar to what happens in a queue, in a ticket window, right? What happens in a ticket window? When this particular thing goes out, all of these elements will need to move front. So you'll have to run a loop and move all of these elements to the front. That's what this says. No shifting needed after deletion. So if there was a queue, shifting was happening. If there was a queue where a shifting was happening, doesn't happen in a queue, right? As I said, we are a shiftable queue in a linear queue, right? We are not taking a shiftable queue in a linear queue. We are taking a normal queue where front is moving forward. If we would have taken a shiftable queue, then the shifting would have cost us order of n. But in a circular queue, that shifting is not needed. That is what this is trying to tell. Now, in the circular queue, there is one more question that is from the PYQ. Suppose a queue is implemented by an array. Write an algorithm to insert a new element at the kth position of the array. That means if I have a queue, circular queue like this, then at the kth position, I want to insert an element. Suppose at this position, I want to insert an element. Then what is the algorithm for this? So this is the algorithm. Again, I'll not go through the algorithm. It is very easy. All you need to do is you'll need to push all these elements. Suppose this is my front and this is my rear, right? So this front and this is my rear. So this front will go on like this to the rear, right? So if this front goes on like this to the rear, then all you need to do is what is happening? Something is happening. Oh, the comment is not removed from the screen. Sorry for that. Fact. My first time with this interface also, I'm not sure how to remove it. Okay, I'm so sorry. This was through the entire lecture, I guess. But yeah, I'm sure with the PPT you can make out once you get the PPT. But I'm sorry for that. This is the first time I'm using this, so I didn't realize that this was on the screen. So what I'm trying to get at now is that the circular queue that we were doing, right? We were saying that there was a front here and there was a rear here, right? So there was a front here, there was a rear here, and this front and rear are actually looking like this. So from the front to rear, this is moving like this, let's say, right? So when front and rear were same, they were here, and then we were doing some NQs. So rear was moving forward, and finally rear came here, right? So that is what this current queue looks like. Now we are saying that I want to insert something here at this kth position. So what I will need to do, I will need to shift all these elements, right? This element, and this element to here, here, and here. That means this position now will become free. And in this position, I will insert my target. So I will have to run a loop backward from here to here, to here, to here. Right? I'll run a loop backward, and then I will actually do a this one. That is I plus 1 is equal to I. That is the next element on the index. I will say that it is equal to the previous element of the index. So it will get shifted, and therefore this element will become moved, and this space becomes free for me. I will insert this space here. This is what I do here. The insert happens here. And because I moved my rear, I will have to adjust rear to rear plus 1. And that's all that I need to do from a circular queue standpoint for this particular question. Define queue and its applications. Define queue, what did I tell you? Definition means that template. One is principal, input, output, application. If you remember this, you will see that this answer is exactly like that. Application of queue is, you know, that in printer scheduling, in CPU scheduling, queues are actually used. So you can put either of that as an application. Deque, some of you have it in your syllabus, some of you don't. So I don't want to spend too much time on deques. It's a large topic. Even double-ended linked list, that's also a larger topic. Both these topics, some of you have, some of you don't have. So while the pack, the PPT here contains everything that you need to know from a examination perspective, some of you will have this, some of you will not have this, right? But then have a look, depending on whether your class actually did this or not. This particular, whatever I'm discussing right now, becomes important. Insertion and deletion are allowed from both the ends for a double-ended queue. All of you know that. A double-ended queue is what? Normally a queue is what? Normally a queue is where insertion happens from here and deletion happens from here. But suppose insertion can happen from here and deletion can happen from here, right? Then we have what is called as the double-ended queue. So see here, the insertion happens here, deletion also happens here. Insertion happens here, deletion also happens here. So this becomes a double-ended queue. Now assume a situation where I say that, okay, I have a queue. You said insertion can happen here, deletion can also happen here. Again, insertion can happen here, deletion can also happen here. That is called a deque. But if I say that deletion I will allow only from one side, then it becomes an output restricted queue. It becomes an output restricted queue because output is not allowed from both the directions. It can be any direction that I have wiped out, not necessarily the right side I wiped out. You can wipe out the left side, but at least one side should have the output. Both the sides cannot have the output. Now, if I take the other angle, that if my input, instead of both the inputs, I will say that the input happens only from any one direction, right? Then it becomes an input restricted queue. So that's the input restricted and output restricted queue. And if you think about another combination, let's say that you said we said that this is how the queue should look like. This is how the queue, double-ended queue should look like. And now if I say that I'm not going to allow this, then what does this become? This becomes a stack, right? So it behaves like a stack. It behaves like a stack. Now let's take that I take it like this. This was the actual double-ended queue. Now in this actual double-ended queue, if I remove this and I remove this, then it is still a double-ended queue, but it becomes a queue, a normal queue, right? So basically a double-ended queue can behave like a stack or a queue. So this can be an MCQ where deque can be asked that which particular data structure behaves like a stack as well as a queue. So that's on this particular topic. Now the operations on deque, it is all here, and it is the same concept. So from a modulo standpoint, again, you will be moving here, right? So whenever you come here, you'll have to move here. So you'll have to apply a modulo. So I'm not going to go there and explain it again. All of the algorithm is here. And again, if you need more inputs, please ping me separately. I can anyway give you those inputs. But remember one thing, that in a DQ, the insert operation is similar. Insert operation will be two kinds of insert operation. Why? Because DQ, if you see here, in a DQ, you will have insert possible from here, insert possible from here. This is what? Front. This is what? Rear. So the insert can be possible at the rear, insert is possible at the front. Whereas in a circular queue, you only had NQ because insert was possible only from here, right? So don't you think insert possible for a circular queue is happening from the rear? That means that these two will be having the same signature, same body. You don't need to worry about the algorithm. If you know the circular queue NQ, then insert rear of DQ is the same as the circular queue. See it, that you are inserting from here. Don't you think this is the same as NQ? Right? So if this is a circular queue and you are inserting like this, then it is the same as NQ. So insert rear is the same as NQ. Whereas insert front is new. This insert front is new. This was not there in a circular queue. DQ has that. Right? So this insert front is what is written here. Insert rear, this is something that is copied from circular queue. This is the same algorithm copied from circular queue. See, there is rear plus 1 modulo size. We were talking about that, right? So that's one thing you need to note. Similarly, from a delete standpoint, right? From a delete standpoint, again, the same thing will apply. So suppose this was a DQ. I'm saying that DQ is possible from here also. Now, don't you think that DQ from the front, this is front, right? Don't you think DQ from the front is the same as a circular queue? So the delete front is actually a DQ for a circular queue. But there should also be a delete rear because it supports a rear delete also, and that is the new function. This is the new function that we have written, and this is the old DQ function which we have kept for delete front. So do not reinvent the wheel when you are asked to do DQ. Please utilize your circular queue functions to actually not repeat what you have already done in a circular queue. So learn circular queue and utilize that for your DQ. Now, peak. Again, if you are peaking a queue, you are peaking the front of the queue. So if this is the front, right, for a normal queue, this peak was possible. But for a DQ, I can peak from here also because my rear is also going to be an exit criteria. Front is also going to be an exit criteria. So I said that peak happens through the exit points. So front and rear are both exit points now. So I can peak the front, I can peak the rear also. But peak the front, don't you think is the same as the normal peak of a circular queue? Because for a circular queue, exit happens from here. So peak will be peaking this. So this get front and peak will be the same signature. Right? And get rear is new. And is empty and is full are, is empty is same. See, is empty is going to be the same here as is empty here. But is full will have a different kind of a concept where we will say that if, let's say, we have elements here, 13, 15, then my front is here, my rear is here, right? So don't you think this queue is full? Yes, this queue is full. So front equal to 0, it is at 0, and rear equal to size minus 1. And therefore, we can say that this is the condition for full. But there can be a situation where my rear is here, my front is here. Same, let's say the elements are populated like this. But my rear is there and front is here. Then rear is not equal to size minus 1. See, front is not 0 and neither is rear size minus 1. So this condition will not hold. But still, still the queue is full. So what will I do? I will say that I will take rear plus plus, and if this rear plus plus becomes equal to my front, then I can consider this as full. So that is what I'm doing. If my front is equal to, see, if my front is equal to rear plus plus, right, then I will consider it as full. But whenever you do plus plus, what did I tell you? You have to account for the circular nature. So I have to do a modulo size to account for the circular nature. So ultimately I'm checking this, but when I actually am at 4, I will need to move it to 0. And that is why I will say that my rear plus 1 modulo size should be equal to my front, rather than saying rear plus 1 equal to modulo size. Easiest way to remember is whenever you do plus 1 for anything, rear, front, whatever unit you are taking to control the index in a circular cube, always remember to do modulo size. So that's on the Deque operations. Questions? A linear list in which elements can be added or removed at either end but not in the middle is called Deque. And then in the middle also linked list, right? Either end or in the middle is a linked list. Either end but not in the middle is a Deque. That's what this particular question is. Next, what are the types of queues? We have a simple queue, which we know. We have a circular queue. We have seen that. Deque, we have seen that. Priority queue, we have not seen. You can put it as a priority queue. And you can say that the queue is enqueued or dequeued based on the priority of the element rather than the position of the element. That's all. If this question comes in terms of what are the different types of queues. So that was all from a this standpoint, queue standpoint. We are coming to linked list. Please tell me what's up. I don't see any questions other than my goof up. So anything that you are not understanding, anything you want me to repeat, or should I go ahead? Please put go ahead or repeat in the chat box so that I can understand. Okay, 1 minute. Right. So let's move on. What is the time? We are bang on 4, so we are in time. We have 2 more things to do: linked list and trees. Linked list. I'm sure most of you know about linked list by now. You have done your practicals. We have a data section. We call this a node, and we have something called as the data section, which can contain several data types. It can be an employee data. It can be whatever you want to choose. It's not necessarily one single data like you see on the screen. 15 is single data. It's an integer. It need not be an integer. It can be a complex data type also, right? It has a data section and it has a pointer section. A pointer that points to the next node. A pointer that points to the next node. This node also has a data. This node also has a pointer. So in this way, we create our payload. These are called payloads. These nodes are called payloads. And we stitch them using the pointer. Right? This pointer is typically called as next. And in order to start to this particular node, in order to get this particular node, we need something called as the head. So this is our head, which actually gets the address of 3200. So head actually has 3200. And head points to this particular node. And if we can get into this 3200 address, we will get to 15, which we want. And if we want the next address, next particular 3, then this address helps us to go to 3,600, where we will get 3, and we can further go to 4,000, where we will get 17. We will further go to 4,400, where we will get 90, and we can further go, but we cannot go because this is null, signifying the end of the list. So this is how a linked list works. It's very simple to understand, very simple to code also, but the main thing is, what all do we do in a linked list? We traverse. Please note these. When you traverse a linked list, you are taking the head, and then you are going here, then you are going here, then you are going here, then you are going here. So you are doing n iterations. So that's why this is order of n. When you are inserting, then you are inserting at, when you are inserting, you can insert in 3 different ways in a linked list. You can insert at the beginning of the linked list. That means you will put one more item here. Your head will start pointing here, and this will start pointing here, and this entity will be broken. Right? So that's what you inserted. How much complexity? It should be an order of 1 complexity, because you don't need to traverse anywhere, right? It doesn't depend on the size of the linked list. It will always be executed in the same amount of time. So that's why this is order of 1. If you do it at the end, if you insert it at the end, that means you are inserting here, right? If you are inserting here, then what are you doing? You are creating one more node, right? Here, this null will now refer to this particular address. This null will now refer to this particular address, and this will become the new null, right? And this, in order to do this, you have to reach this node. How will you reach this node? You only have head pointing here or here. How will you reach this node? You will have to go through all this traversal. That means whatever is the total number of elements will be your time complexity. So that is why you have an order of n. And if you want to insert at this position something, then let's say you want to insert this here, right? So what you need to do is you'll need to push this address from not pointing here to pointing here, and you'll have to put this address to point here. And then you'll also have to break this particular pointer or this particular link. And this takes how much time? So you have to move from here to here to here to here before you can get here. Now this particular point could be easily here, or could be here, or anywhere. So that means it is an order of n. It depends on the size of the array. So that is why at any position it becomes order of n. On the same logic, deletion will also be order of 1 at the beginning. Deletion will be order of n at the end. Deletion will be order of n at the position where it is supposed to be. For a search, if I'm searching for, let's say, this element, right, I will have to go from head, and I will have to move each element to search for this element. This is not the element, my bad. I'm searching for this element, but I'll have to go through the pointers actually to get here, and then I will get this. This could easily be here or here. That means I'm looking at a size of n. So my search is also going to be an order of n. If I'm supposed to update a particular value, let's say I'm supposed to update this to 15, how will I do it? I will again need to come from head, go all the way to here, come here, and then update it to 15. So which means this could easily be here, here, anywhere, depends on the size of the array, and hence it will also be an order of n. So from this particular slide, the takeaway is what are the various functions that are possible in a linked list, and what is the time complexities. Next, again, this I will not go through in details because this is the algorithms for traversal, search, update, all the operations that you saw in the last slide. We are talking about those operations, how they are implemented through an algorithm. This will comes. Be very careful about linked list. Linked list, please do not leave anything. Whatever is here, please study all of it, right? So if you actually take this PPT and study, that's all that you need to study. All these operations will come and comes. for a linked list. So this is something. So these are all siloed operations, right? I will say that, okay, how do I, by the way, do you remember that table that we discussed earlier where we talked about the operations, right? If you see the operations, let me come there. Yeah. So if you see that we are discussing linked list now. So insert can be done at the beginning. We saw that. Insert at the end. Insert at any position. Delete also follows the same line, right? We will also need a get, and we will also need an isEmpty. All these operations should be available for a linked list. But all these operations, we have anyway done the algorithms here. What will also be helpful is if you can stitch these to create a linked list, right? So all of these are fine. These are independently handling a lot of things, right? A delete 3 operations, delete at beginning, delete at end, delete by key. Whenever for linked list delete or insert comes, it will always come in 3 pairs. If insert comes, it will come with these 3 pairs. If delete comes, it will come with these 3 pairs. It typically will not come with 1 pair. You will have to do a delete beginning, you'll have to do a delete end, you'll have to do a delete key. Both insert and delete for linked list 3 plus 3, 6 algorithms. Please take a note of it. Also, understand what is happening during a insert operation. Do not miss out on this part. Let us say that when we are inserting at the beginning, right? So let's say here we are inserting a node. If we are inserting a node at the beginning, then this head will be broken and this head will now point to this. So did we change a pointer? We changed the pointer. So count it as 1. And we will also have to tag this to here. So did we change this also? Yes, because this was null and we changed it to point to a valid address. So this is my second pointer. So how many pointer operations are done? 2. Important for you to understand for the number of pointer operations is going to be 2, because the previous one needs to be changed and the current one needs to be adjusted, right? Similarly, for delete, the pointer operations will be not 2 but 1, right? Why? Let us take a delete. Let us try to delete this node. What will happen? All I need to do is take it here. That's the only pointer adjustment I am doing. I'm not doing any more pointer adjustments. I'm not taking out this, right? What I will do is I will free this from the memory. Then it will automatically be taken out. That's not a pointer adjustment. I have created this using malloc, so I will use free to actually free this, right? So that's what I will do. See, here we are using this free, right? So we are not doing any pointer adjustment for the deleted record, right? We are not setting it to null. Now, so that means that for pointers, for delete, it will be only 1 operations that is being adjusted. Next, as I was saying, all of these are siloed in nature, right? You have insert 3 times, delete 3 times. So what? If I ask you to create a linked list with, let's say, 6 nodes, 6 node linked list, what will you do? What will you do? You will do this. Enter the number of nodes. Read the data of the first node. Create the head node. Okay, so I create the head node. Next, head node data is equal to head.data. Head is pointing to somewhere, right? That new node. That data portion is equal to the input data, whatever came from the input. And the head next is equal to null. That is what you wrote here. Now you are saying temp equal to wherever head is pointing. So this particular section you take inside temp also, right? And then you say for I equal to 2 to n, right? You are supposed to create, let's say, 6 nodes. So you are saying now 2 to n, because 1 node is already done. Head is pointing correctly. All you are going to do now is move this temp and create the next 5 nodes. 1 node is done. 6 nodes what we created. So you have to create 5 nodes like this, right? So that's what you are doing here. So for 2 to n, what will you do? Create a new node, and that new node's data is equal to the input. You'll take an input for the data, and the new node's next is equal to null. So you'll say this is equal to null, and you'll have to adjust this null. This null now needs to be pointing. See the temp next. This is temps next, right? That is equal to the new node. So that new node, that means it is now pointing here, temp next. And now that you have pointed this to here, your new temp will now not point here. New temp will start pointing here, because now this is your last node. So from the last node, again you will create, again the loop will go on like this, and you will create the next node, the next node, the next node, till you get 6 nodes. So this is how, when you are given to create some nodes for a linked list, you are not using any functions, right? You are not using any operation like display, traverse, or insert at beginning or insert at end, right? You are creating the nodes in one shot, right? Through a loop, you are creating the nodes in one shot, and you are actually displaying those nodes back to the user. Here the display is not there, because the question is, how do you create a linked list with n nodes? So take n from the user and do this. Remember this temp is important, right? Initially temp will point to the first one that you created, then you will run a loop with 2 to n, and every time you create a new node, the temp will start shifting from here to here to here to here. Temp will start shifting, and temp will hold. Basically temp is pointing to the last node, so that you can take temp and actually add the next node. So that is what this creating is going to happen. This one is a very important question. ADT using linked list. Any ADT, let's take stack. Can you create a stack using linked list? We have created a stack using what? We have created a stack using array, right? So we created a stack like this, array. All this was an array, right? For us, this was a 0th index, 1th index, 2th index, 3th index. But can we use a linked list to create a stack? We can, right? What we'll need to do is we'll need to create the operations of the stack using linked list. What are the operations of the stack? Push, peek, isEmpty, pop. These are the operations. So push, how will you do? Let us see push, how will we do? So push, we will say that create a new node. Okay, we create a new node. Then new node data equal to value. So data is equal to value. Then the next is equal to the top. So top is pointing somewhere, right? Let's say top is already pointing to something. Let me draw it in a different manner so that it represents a stack, and you will understand. Let's say I have a node here. This has some value, and this is null. And the top is actually pointing here. Now I say push. So a node gets created here. Value is this, right? This is a value. New node next is equal to the top. So it's next. This next is equal to wherever the top is. That means wherever this is, right? So it is pointing here. Now we are saying that top is equal to the new node. That means I have shifted this pointer here. Top is equal to the new node. Don't you see this is now coming up as a stack? Right? This is the last item that was entered. That's why top is pointing here. Right? Now, if we add one more item, what will happen? Create a new node. Okay, create a new node. Then insert the value. Okay, insert the value. Then what will happen? This is going to point to top. Where is top pointing? Here. So this will point here. Right? And then what will happen? Top will need to point to the new node. So top will go here. Right? So this is what push is happening. Similarly, you can do a pop. When you do a pop, what you need to do is you will need to create this top. You will need to push this top. That is, you will need to create this kind of connection and omit this connection. If you omit this connection, you will lose this value. Right? So what you need to do is you store it inside temp. Put this inside temp. Right? Put this inside temp. And this item, this value, right, is what you need. So that you put it inside some variable called item. That's all you need. Then you will adjust this top. This top will be going here. Top.next. and then you will free this. Actually, you will free this 10th, right? Which is basically pointing to the same thing. So it's going to free this also. And then whatever item you had stored, right? Whatever item, that value you had stored here, na? That item is the value that you wanted. You had stored it already. That you are going to return back. So this is typically POP. I'm going a bit fast here. In my lecture, we will see a lengthy kind of an explanation where we will go through each step in details. But I hope you can understand that we are trying to implement a stack using a linked list. And I was trying to draw it in the same manner as stack looks. And with that, I think you can understand how the item is getting at the top of the stack. That's what you are trying to do with your push and pop. Right? So this is from creating a linked list or using a stack through a linked list. We have used stack using arrays, but we also have to use stack using linked list because that gives us much more flexibility. In fact, I think there is one question which will talk about the advantages of stack to be created using linked list. We will come to that, but let's see other questions. If a new node is inserted at the front of a singly linked list and a pointer to the head node is already available, what will be the time complexities? We have seen this, right? So this is my head and this is my nodes, right? And a new node is supposed to be inserted here. What is the time complexity? Order of 1, because I don't need to traverse through any of this. I will just do an insert order of 1. Now, if we want to add it to the tail, then it will be order of n because I'll have to traverse through all of this to add it to the tail, right? So that's why it will be order of n. And if I want to remove the first node, then the first node can be removed just like that. I just need to adjust the head to here. So again, it should be order of 1. I don't need to traverse. And this we have discussed in our WhatsApp group also. Yeah, see, I was talking about this. Linked list is preferred than arrays. Of course, linked list will be preferred because memory is, for an array, it is fixed, but linked list, it is dynamic. You keep on adding next. You are free to actually continue. Insertion deletion in an array is costly. Why? Because if you insert in an array, if you want to insert here, like let's say 7, 9, 15, 1, 2, 3 is here. And I want to insert something here. I want to insert 27 here. What will I have to do? I'll have to move 3 here, then 2 here, then 1 here. This will become empty. 27 will go here. So you see that is an order of n. So it is costly. This is costly, right? But this will be fast. I just need to adjust the pointer. And because all of this happens, this is more flexible. Linked list is more flexible because it can either grow or shrink, right? So that is what is the linked list over array. Now, what does null pointer indicate in a singly linked list? Null pointer indicates the end of the list, right? We all know that. So that's what the question is particularly talking about. Next, double linked list. I'll not go through details as most of you may not have this. Depending on whether you have this in your syllabus or it has been taught in your class, please feel free to do it. But the traversal of a double linked list is the same. Order of n will be the traversal because it will have to go through from this head to here, right? It can also use this tail to go backwards. So that's the beauty of a double linked list. You can go backwards also if you have the tail. But that still will be order of n. This will be reverse printing. Insertion, addition, insertion here at the beginning. Insertion at the beginning is order of 1. Insertion at the end is order of n. And insertion in between is also order of n, just like your normal single linked list. Deletion, same thing as normal linked list. Searching, if you want to search, you will have to go like this and finally might be finding the element here. So which again will be an order of n. Updating, you might be updating this. Again, you have to go like this. So you will also have an order of n. So all of this is the same as what it was in a single linked list. Only a double linked list, you have to remember that there are both way arrows. So you have a next and you have a previous. So previous is also here, next is also here. It points to the previous node as well as it points to the next node. And if you have a tail, nothing like it. If you can have a tail, then you can actually go like this. Otherwise, you have to go from here to to actually trace your route back, right? So you can trace back, which is not possible in a single linked list, but that trace back means that you have to reach somewhere from where you can trace back. But if you had a tail, then you can actually start directly. You don't need to go from here to tail, right? So tail is also there. Some double linked lists don't have tail, some double linked lists will have tail. Depending on the question, you'll have to answer. This anyway is there for whoever it is in the syllabus. I've put it in terms of the algorithms. Will not explain that, but these algorithms will be very simple to do once you understand what you are doing. Again, I have tried to see that whether it is the same as a single linked list, then you don't need to even worry about memorizing this. If you know about the single linked list, how it happens, then traverse, update, and head will be the same as a single linked list. Okay, now this is the same thing, insert at beginning, insert at end, and the insert at any position, insert at any position. Then you also have the delete at beginning, delete at end, and delete at any position. So these are the 6 algorithms that may come if you are talking about double linked list. Again, as I said, they will come in 3 pairs. So if delete comes, delete end, delete key, and delete beginning. If insert comes, insert end, insert beginning, insert at this one. Nothing will come with separate. All 3 of them will come together. So that's the questions that I felt was important. Any more questions on the chat? Can I move on to the next and the last topic? We are at what time? We are on time. We will finish off before, I guess. Please type if I can move on. Okay, chalo. Last topic. 2 types of trees I have depicted here. Most of you might get confused because you're seeing trees for the first time. So tree is, first we'll talk about a binary tree, in which it means that there has to be a binary tree can only have 2 legs. One node can have 2 legs. What resides in those 2 legs is not important, right? So it's not important what resides in those 2 legs, but there should be 2 legs. In case there are not 2 legs, that is also fine, but it cannot be more than 2 legs, right? It cannot be like this. That is what is a binary tree. There is absolutely no ordering of these elements. These elements need not be ordered in any shape and form, right? And I'm not sure if you are able to see. Let me zoom it, and then you will be seeing this, right? So there is absolutely no correlation of the values that the left node has to be this, right node has to be this. That's what is binary tree. Binary tree says that I am a binary tree. I will only have 2 branches. That's what binary tree says, right? There is, see, 27 is here, but 23 is on the right side of 27. We were talking about the right side having only higher elements than 27, but that's not what is a binary tree. That was a binary search tree. So that's the difference. So this is the binary search tree, right? In this binary search tree, the same data, if I represent, it will be like this, that this side will be always less than 27. This side will be always greater than 27. Every left node, the left node entire tree will be greater than less than 27. That means if I take 18, leftmost entire tree will be less than 18. Rightmost entire tree will be greater than 18. That is what is a binary search tree. So how many types of trees are possible? Important for us to understand how many types of trees are possible. 1 is a complete binary tree. All levels are filled except possibly the last, and the last is filled from left to right. Last row is filled from left to right. So ideally, this is not a complete binary tree. Why? Because this should have been here. Left to right means it should have been here. Right? So all the levels should have been filled. This should have been here. So that is what is a complete binary tree. Right? These two nodes should be left to right. That means it should have come here. As I said, there is no reason why you should put it here. Right? You should actually put it here. Here rather. Then this becomes a complete binary tree. Full binary tree, every node has either 0 or exactly 2 children. This is full binary tree. Every node, no, actually not, my bad. Because of this element, this node is, no, this is also 0. Yeah, I am right. This is a full binary tree. Every node has exactly 0 or 2 elements. That is a full binary tree. Perfect binary tree. All internal nodes have 2 children and all leaves are at the same level. All internal nodes have 2 children. All internal nodes. So this is an internal node. They have 2 children. That means this has 2 children. This particular one has 2 children. This particular node has 2 children. All internal nodes have 2 children and all leaves are at the same level. Here leaves are not at the same level. This is at level 3 and this is at level 4. So all leaves are not at the same level. But here it is. All leaves are at level 4. Right? This is first level, second level, third level, fourth level. All leaves are at the same level. Balanced binary tree. Balanced binary tree, height difference between the left and right subtree of any node is at most 1. This is a balanced binary tree. Why? Because left subtree has a height of 3. Right subtree has a height of 4. So 4 minus 3 is 1. Difference is at most 1. So that's why it is a balanced binary tree. Binary search tree, you can see here all the left is less than the node, all the right is less than the right, greater than the node. That is what is binary search tree. So it is important for you to understand the definition of all of this, right? May not be that you will be asked to draw it, but the definition wise, you should know what is what. Binary tree, 2 more slides we have. Let us complete it. This is traversal. This definitely will come wherever tree is there in the syllabus. Traversal will come, will come, will come. I cannot stress more on this. Right? So let us see traversals here. Binary tree traversal. Since the binary tree has no logic of elements, that's why these are alphabets and not numbers. They can be numbers, but the numbers will have no meaning in terms of sequence. So from a binary tree, if we do an in-order traversal, for an in-order traversal, if you want to remember what is in-order traversal for a tree, the way I remember it is that my root signifies the operator. Now, for in-order, where is the operator? In between. So the root should also be in between left and right. So that is my trap. Right? In order, do not ratta or mistake or get confused. Use this logic, you'll never be defeated. In order will always mean that, okay, my plus has to be in between, and plus is an operator. Operator is equivalent to root. Left, root, right. Right? Similarly, my preorder is what? Preorder is plus AB. Plus AB means operator is here. And I said operator is the root. So root, left, right. That is my preorder traversal of the same tree. And postorder is what? Postorder is minus, A, B, plus. Plus is my operator. Operator is the root. So root, and then I will put left and right here. So that is my post order. So this, and this, you will never forget if you remember it like this. Right? So that is, and that's how it is designed also, right? So you will see how that is designed. Now, when we are doing this DBAEFC, we are doing an in-order traversal left root right. So what you will do is you will go left from here. If you see that the left still has a left, if you see that the left still has a left, you will go further left and you will get this D. Right? So the left still had a further left, so you got this D. And that's how you got this. Because the final D did not have any more left. So you cannot go any more left. So go on till the left, till you have no more left. Right? So that's how you get to D. Then, once you are finished with that, whoever helped you to finish your left, you'll have to finish what? You'll have to finish the root. So you did left, you have to do the root. Right? So go up and take this root. That is how you get your B. Now you have to go down and take the right. Now, if this right had a left and right, then you'll have to go left, right till you get a final right. You cannot stop here, or you cannot visit this node if you have branches here. You have to cross it and go to the leaf level if you have branches. In this case, we don't have branches, so which is okay. So we will take E as our next output. We will visit this, we will take this. So this is done. So left root right was done. But remember, we had come here from a left standpoint. So this particular transaction's root is pending. So we have to take out the root. So we will take out the root here. Right? And this particular transaction left, we did so much of left we did. Then we took out the root. Then we have to go right. So when we go right, as I said, if you have a right, I could have taken C, but I can't because this is not the leaf. I told you, right? If you have a node, you will have to go till the node. So you have gone right. Yes, agreed. And this was your left, this was your root, and this was your right. Yes, agreed, you have come right. But this right has a leaf. And because it has a leaf, I have to go here. So from this, I again start my left journey. So I will go left. I will go left means I will get my F. Now this F doesn't have anything, so I will go up. Why did I come to left? I came to left because I was starting a left root right. So I have to go back to the root. So left is done, root. I have to go back to the root. The root is saying, take me. So take me means C will come here. Right? And then I will go right. Right, there is nothing. So this becomes over. So this left root right is over. But then we had started left root right. So this left root, if this left root right is over, this entire left root right is also over. And therefore we come out. So that is how we will get DBEAFC. If we do a pre-order traversal, which is basically a root left right. If we do a pre-order traversal, which is root left right, then if you do a pre-order traversal, which is root left right, then because we are visiting the root, we will take the root, we will visit the root. So root is first, we will take the root, which is A. Then we will go left. If we encounter a root, we will take it. Whenever we encounter a root, we will take it. So when we go left, this is also a root. So we will take B. Again, we will go left. From root, we will go left. Right? So this left is also a root, which has no leaves. So we will take D. Whenever we encounter a root, we will take it. Then left, root, root, left, and then we will go right. When we go right here, this is also a root. Right? For us, this is also a root. So we will also take this because this root has nothing here. So we will take this as E. Now we have finished our root left portion. This was my root and this was my left. So now we are going on the right. So we have to go to the right section. In the right section, this is a row. This is a root for us. Whenever we encounter a root, I told you we will take it. So we will take this. Now this root is done. So we will go root left. This left we will take or not take. This is also a root, right? So we will take this F and then we will do the stack unwinding and we will not have any further nodes. So that is the pre-order traversal. Next is the last, which is the post-order traversal. In the post-order traversal, we will do left, right, and root. So left, right, and root is going to be looking like this. We will go left. I told you if you go left, then go on till the last node. So we will take D. Then we will take the right. So the right is here. So from here, I have to go here, right? So the right, we have to go here, which is E. So we will go here, E. And then we have to go to the root, left, right, root. So we will take this. We have taken this and then took this. So we have taken DEB. Now this left part is done for this, right? So the left part is done here. This part is done. Now right part needs to be done. So I cannot take A. I will have to go to the right part. So in the right part, what will I do? I will need to do the same thing, left, right, root. So in the right part, I have to go left. So I have to take this. I will take this left, then right, there is nothing. A root, I will take this, C, and then because this right part is over, now I can safely take this root, which is my A. So that is how your post-order traversal is happening. Hope you have understood this. Otherwise, you can do a rewind of this thing and repeatedly see it. Binary search tree. If we actually do the same thing, this is the last topic. If you do a binary search tree traversal, then the ascending order of the elements will come out if you do an in-order traversal. That is the important thing here, right? So please understand that if you do an in-order traversal of this binary tree, then what will come out will be the ascending order of this particular list. But this is only possible in a binary search tree. It is not possible in a binary tree, right? And no other search orders will come out from a binary search tree, neither a postfix or an infix or post-order traversal or in-order traversal will not create any other search orders. The only search order that is possible is an ascending search order. When it is possible, when you do an in-order traversal. What is an in-order traversal? If you remember, in-order traversal is left root right, right? So if we go a left root right, then the first element we will hit, I told you, right? If we have to go left, then we will have to go left like this. We will have to go left like this from here to here to here. All the left till we reach the node. So this is my left. I'll just zoom this so that you can see this, right? So this is my left. Left root. So I have to take this. My left is done. I have to take this. So left root. See, left root. And then I will go right. 15. This is also done. So this is done. Why did I reach here? I was going from here, trying to go to left. That means after this, what should I do? I should take the root. So root is also gone here. Then I will go right. From here, I should go again left root right. So I will take 21 from here. Left root, I will take 23 from here. Right, 24 from here. Then I will come back at the top. I have finished this section. So my left is done. So I have to take out the root. 27 I will take. Now I have to do this part, right? I'm on the right part, left root. This was the big left. Then this was the root. And now we are talking of the big right. In this big right, we have to break it down into smaller things. So we have to go from left, and take this 35. If we have this 35, then the root is left root 36. So we will take 36 out here. Then we will take 39 here. 39 here. Then we have finished this. So left root we have to take out 41. Then we have to take out the right part, which is my 50. But I will not take 50. Need to go to the leaf. 45. 45. Root I will take out 50. And then I will go to 55. I've taken out all my elements. And you see this entire thing is sorted in ascending order. So an in-order traversal of a binary search tree creates an ascending order. So with that, that's all I had to cover. 90% of what you can expect in your CA should be from these, because I have taken all your syllabus. I've seen what all are important. And I'm hopeful that this would be covering most of what you want to actually understand and learn. So spend some 2-3 hours with the PPT. I think you should be good. Any last questions? Yes. So your exams will be either tomorrow or day after, I know. I'm aware of that. But all the best for your examinations. But please read the PPT. I'm posting the PPT in the WhatsApp group first. And then for people who might not be joining these channels, these WhatsApp groups, they're also part of your class. So I'll also post it in the classrooms. Anything you want to probably comment here? Otherwise, feel free to WhatsApp in the group itself. All okay? Making of a tree with a list of numbers is not that relevant at this stage. It's doable. I mean, it's a simple thing. It should have been part of your standard stuff of traversal. It's the ulta of traversal, right? I hope you can understand. Since you have done traversal, you can make a tree using whatever logic you can do, right? But then I leave it to you. I don't find that as important, which is why I have skipped it. Should we sign off? Okay, chalo, all the best.